My name is Anissa Lopez, and I'm the project leader for Project 23126, called Solar-Powered Aquaponics Design Exploration, otherwise known as Spade.
My name is Diego Salido, and I'm an environmental engineering major.
My name is Anissa Lopez, and I'm an environmental engineering major.
My name is Ashley Duncan, and I'm an environmental engineering major.
Hi, I'm Kayla Bansback, and I'm in chemical engineering. In the scope of our solar system, Mars is widely considered to be the next most habitable planet. This has led many people to examine the possibilities and challenges of an interplanetary mission to Mars, which is what inspired the Spade project. The Spade project aims to provide an efficient and reliable alternative to the current methods of feeding a crew of astronauts. Supplying a hypothetical crew of 4 astronauts with proper nutrition for a 4-year mission on Mars, in addition to the 7 months of travel time each way, provides some serious challenges. Due to the 7-month travel time, it is not feasible to rely on regular resupplies from Earth, so one such mission would have to be able to accommodate the nutritional needs of the crew for the entire duration of their travel and mission. The current industry standard for nutrition is freeze-dried rations. Every pound of payload costs an average of $10,000, which means that packing enough rations for the caloric needs of 4 astronauts would cost upwards of $75 million. On average, NASA astronaut candidates are 34 years old, and with that, their recommended daily caloric intake is 3,000 calories, or about a pound of food per day per person, using the current rations. Spade proposes, instead of completely relying on freeze-dried rations, an aquaponics system could be implemented by the astronauts while on Mars to supplant 35% of their daily caloric intake with fresh fish and vegetables. Aquaponics combines traditional farming methods with aquaculture to create a self-contained and self-sustaining system. The system can be scaled up or down depending on the caloric needs and takes advantage of vertical farming techniques to allow more plants to be grown per square foot. The Spade project goals include a self-sustaining closed aquaponics system on Mars to provide 35% of the daily caloric intake for a crew of 4 people. Automation will be used to reduce labor requirements of the crew to maintain the system. This system will be highly efficient, low cost, and powered by solar panels as a renewable energy source to reduce the demand of resources on a space module.
In an aquaponics system, the fish have the role of providing the nitrogen uptake. The nitrogen input is the fish food. The fish produce waste mainly in the form of ammonia. Naturally occurring nitrifying bacteria convert the ammonia into nitrite. The nitrite is then further broken down into nitrate by another type of bacteria. The water that contains nitrates is then circled throughout the columns where the plants are growing. The plants take up nitrates as their primary source of nitrogen and other essential nutrients. The plants and fish then make up the product of the aquaponics system. This nitrogen cycle is crucial to the success of the aquaponics system. A balance must be maintained between the fish, bacteria, and plants to ensure optimal conditions for all components of the system. As we have established the system, we have been monitoring water quality, including the nitrogen levels. From the left to the right is the ammonia, nitrite, and nitrate concentrations. This is a graph that shows the theoretical trends of the nitrogen concentrations within the system. There's an ammonia peak, then a nitrite peak, and then the nitrate starts increasing. This is what our graph looks like. The ammonia peaked at the very beginning, nitrite peaked slightly after, and the nitrate was on the increase. However, the nitrate levels have been decreasing due to dissolved oxygen decreasing.
When designing our system, we made the decision to use tilapia as our fish due to low cost, high calorie per gram, and because tilapia was readily available for building our prototype system. The calorie calculator includes information on the ideal conditions each plant wants to grow in using traditional farming techniques. This helped us decide the type of plants to grow, as we want to produce as many calories as we can while minimizing the resources used. In addition to gathering information on the plants and fish, we calculated the amount of calories needed for 1 year for a crew of 4 astronauts, which is 1,277,500 calories. This was used to find the optimal amount of plants and fish needed to be consumed to reach the yearly calorie amount. Factoring in the ability to replant after harvest, we found the optimal combination to reach our 35% intake goal. Finally, we were able to scale down our theoretical design in order to produce a small percentage of the ideal system. The prototype has 4 growing columns, each containing 8 plants, all connected to a system containing 12 fish. This is an overview of the original design made. It includes 2 growing systems, one with a biofilter to grow bacteria, and one where the biofilter would be contained in the growing columns. This design was evidently scrapped due to the grow column height of 7 feet not being ideal. This is an overview of the current prototype, which can produce the same amount of produce as version 1. This version is also 7 feet tall, but can be modulated to produce significantly more calories than the first system. We'll go into a breakdown of the fish tank, biofilter, and spinning grow columns. The design is currently patent pending through the University of Arizona Patent Office. Going into the details of our fish tank, this is a 75-gallon fish tank that is currently holding 55 gallons of water for our fish. There is a standpipe in the middle that is used to regulate flow through water displacement and to ensure the fish tank always has the same water level. There is also an initial screen for solids at the bottom of the fish tank here. Water comes through the screen at the bottom and falls through the standpipe on its way to the biofilter. This is a look at the standpipe in the filter. It also is worth noting that the screen pipe that is not pictured is taller than the standpipe so that all the water goes through the screen. This is an overview of the submerged upflow biofilter with a solids removal valve. Water flows through the pipe that connects the tank to the biofilter and then fills the gray bin that is filled with media and a filter mesh, cultivating the bacterial growth.
Our current version of the prototype for the growing columns consists of a structure of 4 shorter columns which rotate about their own axis and are set up around a central growing light. The metal frame in the center provides structural support for the columns and holds the light and motor in place. The columns are attached to the main lower PVC structure by an array of 3D printed pieces and a ball bearing which facilitates rotation and allows for drainage at the same time. There is a similar attachment at the top of the columns, which helps reduce friction with ball bearings and allows for uniform water flow and distribution throughout the column. The motor is attached to the metal frame with a wood structure, and with the help of a pulley generating enough tension, pulls on a conveyor belt that wraps around all 4 columns to rotate them uniformly for even light exposure. The third picture shows our growing columns set on top of the fish tank right before functional testing started.
The theoretical design of our system is based on the assumption that Mars already has an established space module that can provide the necessary resources to start up the Spade system. The theoretical design needs to be 40 times the prototype you just saw in order to achieve our goal of 35% of the average daily caloric intake of our crew. As you can see in this P and ID, there are some additions to the design for the Mars atmosphere. This will include a heat exchanger to maintain the optimal temperature to grow Nile tilapia. The Mars system will also include solar panels in order to reduce the electrical demand on the space module. To power our system, we have calculated that we need 32 solar panels with a 21.8% efficiency, one of the highest on the market. We also are looking to reduce the labor demand of the crew members by automating portions of the system, including the fish feeding, water quality monitoring, and nutrient monitoring that will be controlled using Raspberry Pi.
This is a brief overview of our project economics. Focusing on the prototype side, it costs approximately $1,200 to build, and it produces 2.5% of our ultimate 35% average caloric intake goal. On the resources aspect, the prototype's energy consumption is 3.17 kilowatt hours, and the water usage is approximately 75 gallons. The theoretical scaled-up design consists of 40 times the amount of plants and fish on the prototype, and it would need 32 high-efficiency solar panels to cover its energy needs, which would cost approximately $123,000. The water usage of the system would total approximately 51 gallons per year, considering the scale-up and plant intake of water, bringing the total cost to $171,000.
First major barrier we hit was that we had to redesign our project. The other large barriers we had come across were related to building the prototype. Some of the larger issues included having various leaks in the system. We've had challenges with the motor and tension in the belt. The initial plants that we had wanted to grow were not available to us. And the last big issue is limiting the growth of the algae on the biofilter. Future work on this project would include ways to improve the prototype we created so it would be more efficient on Mars. Some of the improvements would create an automated system that would feed the fish and check the water quality to lower the labor needed. To be self-sustainable, the system would need to have its own power source, which consists of solar panels and backup generators. Having a larger fish tank means it would be necessary to include a heat exchanger to combat lower temperatures. Ultimately, we want to be able to completely answer the question of how we can further optimize the design to increase caloric output percentage to sustain more people or longer duration missions. Here's a list of people we would like to acknowledge who supported and mentored us throughout this project.